And welcome back to the Turd Fur Network. All right, today's video is primarily on potential energy and kinetic energy, a little bit for the most part. But anyway, let's first get into what energy is: the ability to do work or the ability to cause a change. So remember, doing work is when you've done a force through some distance, is what you've done. And the first thing we're looking at is the potential energy, which is, and there's a definition for it, but a lot of people would just think of it kind of like potential energy, think of like stored energy. And we've got all different types of examples there. What does it take to store energy in something? Well, we can actually go through and take a look at each one of these, like elastic, electrical, I don't feel like shocking myself, magnetic, radiant. If you don't think the sun has the ability to cause a change, I encourage you, go outside sometime. Go out, lay beside the pool. Sunscreen is for wimps. You lay out beside that pool and you put on your big smile and get burned to a crisp. That sun definitely has the ability to, quote, cause a change, so to say. Let's see, nuclear energy. Yeah, there is definitely energy contained in those situations, and chemical energy. So we can kind of take a look at several different forms of energy. Now, usually one of the first ones that we start thinking about, at least in terms of school, when we start thinking about energy, is we think about the energy associated with, say, lifting something up or picking something up. When you see this object held up into the air, as soon as I find the camera, this object now has some energy stored in it. Its energy would be proportional to, hey, now that's a good question. Well, let's do something. Let's compare energies. So if I had these two objects and I picked them both up the same height, which one has more energy? Well, it's an easy question. You know that the 1 kilogram mass has the most energy. It's obviously far bigger. Well, how about if we did this? Now, this would be a good question. Is there any way that this little bitty 5-gram one could have as much energy as the big one? Well, in theory, yeah. But guess what you'd have to do? So that these energies equaled, the big one would have to be setting really low down to the ground, and the little one would have to be what? Raised really, really high. So we know that potential energy's got to do with two things. It's got to not only do with how much mass an object has, but it's also got to do with how high that object is lifted. Now, one of the typical, more famous little examples of potential energy is usually what I like to call the can crusher. And here is an example of the can crusher. So when you see this object picked up into the air, on the video I can't pick it up very far, but when this object's lifted up in the air, I've stored energy in this object. This object has the ability to cause a change. What? Don't believe me? That has the ability to cause a change? Well, yeah, it has the ability to cause a change. You see the can? I'm only dropping this like a foot. Probably like whack me right in the face too. Ah! It definitely has the ability to cause a change. It can cause a lot of change. I hate aluminum cans. Not really. I've really got no bias. I bet it's horrible in this video, that cracking, so I'm going to stop now. But we can obviously see that that stored energy has the ability to cause a change. So we're witnessing that. We'll talk more about that in just 1 second. What about other types of energy? Hey, wait. There's a rubber band. As we look at this rubber band, does this rubber band have the ability to cause a change? Well, not right now because there's no energy in the rubber band. But what we can do is stretch the rubber band. And now we can obviously see, ow, it has the ability to cause a change. Now, are all rubber bands created equal? Well, obviously, let's see this guy. Let's have a little bit more beef to, I really don't need to break this monitor I'm on. Obviously, this is a much stouter rubber band than this rubber band. So, anyway, we'll look more at that in a second. Other types of change, energy. Oh, wait a second. Here's a good one. One of my favorites. rubbing alcohol. Fire. So as we sit here, and we'll give this a little spritzer of alcohol. Whee! Little alcohol, and what? We have fire. Ah, hey, little too much fire, too much fire. It's okay. I do this for a living. It'll be all right. All right, so anyway. Wow, that was scary. All right, so anyway, that's an example of energy that has been stored. And I probably need to get away from this thing and back to the video before I hurt myself. So today we're going to look specifically at two different equations, one of which is this potential energy, and this is potential energy due to gravity, and it still smells like something's on fire in here. And so you can look at the equation for potential energy. Mass, gravity. What does Y stand for? Y is referring to how high I've lifted that object. So if I want to find that can crusher a second ago, it's got a mass of 4 kilograms. Gravity is still 9.8 meters per second square. And height, well, let's see, height would be, I'll go ahead and tell you, for that can crusher, it's basically 1 meter is how tall that crusher is. And so if you multiply that across, that comes out to 39.2 kilograms. Now this is kind of neat. A kilogram meter second square, which is a Newton meter, which a Newton meter is the exact same thing as a joule. So 39.2 joules. So there's our equation for potential energy. Now we can go back and think about a spring. And we were looking at a spring a second ago. The basic equation for a spring is this. Potential energy in a spring is equal to 1/2 kx squared. K is what's known as a spring constant. And you can really look at it in terms of how springy a spring is. You see, some springs are much harder to stretch than others. And therefore, they have the ability to store a lot more energy than others do. X, and this is where y'all get messed up. This is literally where y'all kind of get messed up when doing these problems. A lot of times spring questions will give you 2 lengths for a spring. They will give you 2 lengths. So like, for example, right now, this slinky of mine is about 6 centimeters long. That's how long my slinky is. Now I'm going to stretch the slinky out to 20 centimeters. So these slinky problems are prone to give you 2 lengths. So it's giving me 1 length of 6, another length of 20. So what does X actually mean in the formula? What does X mean? Well, X is just how far did you stretch it. So starting here, this is 6. Now it's 20. How far have I stretched it? Well, I've stretched it 14 centimeters or 0.14 meters. So whenever you're doing a spring problem, you're looking for not what the first length is, not the second length. You're looking for how far, ooh, slinky. You're looking how far that the spring was displaced. Vice versa, if it gives you a rubber band, you're going to get the first length for the rubber band, which is about 9, stretch it to 12. So what is X equal to? Well, X would be equal to 3. Now, in terms of what K is just how springy is the rubber band. That's all K is talking about. Not all rubber bands are created equal to each other. Obviously, this one is a much harder one to stretch than the other one. This one, look at this. Hook it between 2 pinky fingers and doingy, 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 doingy. Very easy to stretch. Whereas this one, on the other hand, pinky stretch. Ah! That's not quite so easy to stretch. Obviously, this has a much higher K. This is a much springier spring, so to say. So anyway, I think something's still on fire. So I might want to end this video like right about now. But we'll do one more thing. Then we'll go work some problems. Kinetic energy is equal to 1/2 mv squared. And usually we think about kinetic energy when we think about something that is in motion. And you can look at the equation, mass times velocity squared. And now, one of the big things y'all got to get in your head is, since energy is not created or destroyed, think about this can crusher. Up here, this can crusher has got potential energy. What does that potential energy turn into as it falls? Well, put your finger down underneath that thing. No thumb. Actually, it's a huge thumb. He must have already had his thumb under this thing. When that thing falls, it's going to have a tremendous amount of kinetic energy. So energy is not created or destroyed. Energy just changes form. So in this case, from potential to kinetic. Now, somebody might say, what happens after you've squished up the can? Where did the energy go? Well, usually what I like to do is hit the can a bunch of times, and you'll notice something. The can gets warm and starts giving off heat. And that's what happens. The potential turns into kinetic, which then turns into heat energy, which is the subject of another video. And we'll do another video where we work some of these problems. That's got you introduced to the formulas and the concepts a little. Anyway, you have a great day and stay sexy, San Diego. I have no idea what that means. Thank you, Ron Burke.